Hello, good morning everyone. My name is Estefania Coronado and I am with AutoCAD Foundation in Spain. And today I will be presenting this work that we have performed in collaboration with Università Politecnica delle Marche in Italy, entitled Roadrunner, an ORAN-based cell selection for beyond 5G networks. In order to do so, I've prepared this outline in which I will divide my presentation into 4 sections. First, I will introduce and motivate the work that I am presenting today. In a second stage, I will present the design of the scheme that I am presenting in this work. And finally, I will showcase some remarks from the performance evaluation, and I will conclude the presentation. So as we all know, the current operational networks are transitioning from 4G to 5G, and that is also true from the devices of most of the population. So they are mostly available nowadays in the market, and everyone is, let's say, observing this transitioning from both the user equipment and the operator point of view. As a consequence, what we are overseeing is that more cells are being deployed to increase this network density, and the network frequency are being also, let's say, enlarged, and a huge part of them are being exploded. Of course, a series of technological advances are being deployed to increase the optimal use of network resources, and this happened from previous generation, even before 4G to 5G, and will happen as we progressively move towards 6G. However, in order to fully exploit these improvements and these technological advances, it is mandatory that users are associated to the cells that actually can provide the best performance and not just the best radio quality, as the user association procedures provided by 3GPP tend to. So, as I was saying, cell selection in 3GPP is performed in such a way that it is ensured that all the UEs are connected to good cells, but they don't need to be necessarily the best one. So it is good enough as the traffic that is supposed to be delivered is finally, let's say, reached in the destination. This method that is generated from previous cellular generations actually is due to the fact of wanting to preserve the backward compatibility with previous generations. So, for instance, now in this transition from 4G to 5G, and the immediate consequence is that a UE can get stuck with lower data rates, even if we can find in the network other cells that could provide better performance. In this sense, in following the 3GPP procedure, during the server selection, the network controls the quality measurements from neighboring cells based on the quality levels of RSRP and RSRQ, as indicated in the figure shown in this slide. So we can see how the base station first sets the criteria to trigger these measurements in the UE. Then the UE performs the measurements and reports the results according to the conditions satisfied. And if these conditions are somehow met by the procedures of the base station, then we start the handover towards a new cell. Of course, this is just a simplification of the whole procedure, but just to sketch how this operation takes place in 3GPP. So, as I was saying, as long as the signal quality is good enough in 3GPP, the UE will stay connected to that current cell regardless of other options. And the main problem here is that this procedure does not take into account other policies, other parameters that should be considered, such as cell bandwidth. So altogether, the main problem is that this can lead to an underutilization of network resources and low performance of the UEs. Let's sketch this explanation with two examples. So we can see here in a scenario 1 a single UE attached to cell A, although there is available another one with double the bandwidth. As we can see, the difference in quality is very low. So let's say one person can think that even if we transition the UE from cell A to cell B, the difference in quality will be very little, but actually we will get a higher throughput due to the greater bandwidth available in this cell. However, this will not happen in the procedure enabled by 3GPP. The same will happen in a scenario 2 when we have two UEs and homogeneous channel conditions. But the point here is that if we have two UEs with the same connected to the same cell, and we have another cell available with the same bandwidth, this procedure doesn't take into account neither the fact of load balancing, and as we can see in the second picture, this will greatly benefit both UEs. We can see how the results would look if we measure this in a small test. So we can see how the legacy, the one enabled by 3GPP in scenario 1, will literally reach 10 Mbps, while if we perform what we understand it would be an optimal solution, it will double this figure. And actually the same will happen when we have two UEs for the aggregated throughput of the two of them. So this is actually the motivation for the design of this algorithm that we are presenting today in this conference. So we have entitled our algorithm Roadrunner, and the main objective is to tackle the resource underutilization problem originated from cell selection to achieve better resource utilization, selecting the cells that do not provide only a good link quality but also higher channel bandwidth. So in this sense, we can analyze the requirements, what is a requirement for a Roadrunner and what is not, in order to understand better the design decisions of this algorithm. So for this, I have structured this explanation into a table. So if we look at the left, we can see what Roadrunner does not require. As we can see, no special measurements or new signaling is required for taking this algorithm. So the traditional exchange presented in the first slide could do it, although additional tune parameters as the channel bandwidth will be analyzed. No modifications in the standard 3GPP mechanism are required, so the algorithm is fully compatible with the standard, and of course no changes are required in the UEs. Or in other words, we can summarize this as it will be fully compatible with the operational cells or the UEs available at the market. By contrast, on the right, we can see what Roadrunner requires, and it's the adoption of an NORAM-based architecture, allowing the implementation of deployment of XApps. So an NORAM-based architecture will be key to deploy this algorithm that will be instantiated as an XApp on top of the near real-time rig controller. We can see this in the next slide. So on the left, for the reference, we have included the ORAN reference architecture, where we can see different layers. So we have the RU and the DU on the bottom, and then we have all the part of the protocol stack and the near real-time rig and the non-real-time rig on the orchestration and automation layer. So in this regard, our key part is to have a deployment that is based on this flexible architecture provided by the ORAN Alliance. And in particular, as we can see on the parallelism of the Roadrunner architecture, we will base the Roadrunner X app on top of the near real-time rig, having the opportunity to get the information of the underlying radio technology from the radio network information based. Let's move now to understand a bit the signaling that Roadrunner would perform. We'll have on the left the same figure that I've shown before, while on the right we have the let's say the standard version from the Roadrunner design. So as we can see, we will have in any way the measurement report in exchange enabler between the base station and the UE. But the difference would be that now the serving cell would provide this measurement to the near real-time rig, and then this measurement would be stored in the database mentioned before and read periodically by the Roadrunner X app, which will provide the hand-off inference and would trigger the bandwidth-aware cell selection algorithm. When this algorithm is executed, it will be a handoff request, if needed, that will be directly sent either by the X app itself or by the near real-time rig to the serving cell, and from this moment on the serving cell will trigger the handoff request and procedure as established by 3GPP. So as we can see, no modifications at all will be required for using and deploying this algorithm. This work builds on the procedure for cell selection defined by 3GPP in the TS38.331 that is defined on the bottom of the slide, that defines 6 types of event for mobility and for the acquisition of the link quality, that defines intra-RAD cells or inter-RAD events. But in this case, Roadrunner does not distinguish among the event types, and it just triggers the algorithm each time a new measurement is stored in the database of the near real-time rig. In this table, just for the reference, we have included some lower and upper bounds of the different parameters that are considered in the standard for both 4G and 5G. Now I will start with the description of the algorithm that we have presented in this work. So basically it's considered the same parameters that are used by 3GPP, with the inclusion of 3 more parameters. So on the one hand, what we have is the percentage of physical resource blocks used in the cells and the number of UEs attached in the cells for both understanding the amount of resources available and how much load a cell is. In the same way, we have introduced a parameter that we designed by P that defines the accepted penalty in dBs, and basically defines the radio quality penalty that we are willing to accept if the cell resources on the target cell, on the new cell that is evaluated, would provide a higher performance. So let's start now with the description of the algorithm that I have divided into 2 functions, the one for cell reselection and the one for bandwidth and quality estimation. That basically what it does is to weight the resources available in a cell with the quality of the radio link. So what this algorithm first does is to loop on the list of suitable cells, of course. The first, let's say that initially the best cell is selected as the one that is the serving cell right now, but this is being updated while we get a new cell that has either an overview, let's say a joint estimation of the bandwidth and quality estimation. On the same way, let's say in this loop, we compare the quality of the cells, ranking them and checking those with acceptable quality as defined by the standard, with the only difference that here we assume this aforementioned penalty. So if the quality is not as good as the best one as selected right now, but is, let's say, in the range of this penalty, then we, let's say, make the effort to estimate the bandwidth available and see if we get better results doing this change. So to do so, we have to execute the function on the bottom of the slide, and what we do is basically to weight the link quality with the resources expected in both the current best cell and the candidate cell, weighting the percentage of used PRBs and the number of UEs. And the one with this highest ratio is basically selected, since we assume that the performance would be higher in this case. In case that there is no difference in the RSRP level as designated by 3GPP, then the cell with the highest RSRQ is selected. And finally, in case that the handoff is forced because, let's say, getting far from the current cell and we are not finding any suitable cell as defined by 3GPP, then the best accepted cell is chosen. Let's now start with the performance evaluation. To do so, we have used a real-world testbed implemented on top of 5Gen Power as near real-time rig controller, and we have used SRS Run to implement the radio access and Open5Gs to implement the core network. In the same way, we have defined two scenarios, cell A and cell B, with a different amount of PRBs and different distance, and the same for scenario 2, with the difference that we have 2 UEs here, the distance is the same, and the same amount of physical resource blocks. So as we can see here are the results on scenario 1 on the left part, where we can see that for the legacy one, we have an average throughput of 20 Mbps, while the average in the with our algorithm reaches 30 Mbps. So accepting a slightly worse radio quality, we get to associate to a new cell that provides a better bandwidth. In scenario 2, we have the aggregated throughput of the 2 UEs. The baseline we get is 40 Mbps, while we get almost the double in our approach, since it can significantly improve the performance by load balancing the 2 UEs that we had in the first cell. So as a conclusion, we can see that Roadrunner is a novel bandwidth-based cell selection technology for cellular networks, that the proposed solution leverages a neuron architecture to pursue the handover strategies, and the evaluation on a real world testbed under various channel conditions has shown an almost 2x aggregated throughput improvement with respect to the legacy cell selection of 3GPP. So thank you very much, and if you have any question, I will be very glad to answer you.